This one done. Don't comment, turn on join. Come on, let's go, let's go, let's go. Stay as a participant. Oh man, right. It's taking a sweet time today. Done. All right. Let's share. Oh, there it is. Share the screen. Oh, these numbers. I might need to start locking the door. I've been avoiding it, but you know, I'm gonna let it be for now. It's kind of based on my mood. You know, as long as I'm not if I'm in a bad mood, I'm gonna lock it at the 15-minute mark. Again, I try to make it simple for people. You know, just come here and zen out. I don't hound you. I don't make you do oral, presentations or anything. Like, yeah, I try to keep it simple, but with the way we have the online setup, unlimited attempts, the system is set to take your highest score. There's at most a 10% late penalty. It's either 5 or 10%. I know it's one or the two. Let me see. I think we're kind of in the home stretch, right? We're in chapter 4 on integrals. As usual, if you have questions, feel free to either unmute yourself or type in the chat or the Q&A, and we can make sure to get your inquiry addressed. I'll just say whoever does the most talking does the most learning. The only reason I know this stuff is because I'm always talking about it. And I know this is like an introduction for many of you. Just do your best, and this is a safe space to ask questions. Like, for the most part, I believe in the philosophy. There are no dumb questions unless somebody's intentionally being dumb, but then that's a little bit different. But anywho, okay, so let's get the party started. So last time we did section 4.2. So today I'd like to start with section 4.3, area and definite integrals. So the whole time, chapters 1 through 3, we've been talking about the derivative. We introduced the concept behind it, the formal definition with the limit as h tends to 0, the difference quotient. Then we explored techniques and applications all about the derivative. And so, we basically said that the derivative is the slope of the tangent line at a point. So given a function, we can find a derivative. We explore higher order derivatives, things of this nature. So then here, now we're going to start with the derivative and work backwards, right? And so we're continuing with that idea. Last time I think we said that the integral or the antiderivative is the area under the curve. So like you have a graph, so in a graphical sense, the derivative is the slope of the tangent line at a point. In a graphical sense, the integral is the area under the curve, right? Essentially. Okay. So if we have like a graph, we have a curve, we want to find the integral, graphically, it'll be the area under the curve. Okay. So we're going to take that concept of the area under the curve, take it a step further. A few objectives. Let me see. I know you guys are popping in and out. It's all good. Just, I think we're okay. Let's go like this. Okay. And I feel like I'm always preaching to the choir because I have the same gentlemen that are always here. I do need to kind of submit names for people that have been MIA. So it could happen at any moment. Again, if you feel if we haven't, I need to find my list because I know you guys sent that. That's why I've been kind of avoiding it. But I know some people want to be booted. I just need to take the time to kind of go through that. I guess I just need to make a list. Anyway, I'll worry about that later. Let's go ahead. So a few objectives here. One, find the area under the graph of a non-negative function over a given closed interval. 2, evaluate a definite integral. And then 3, solve applied problems involving definite intervals. Okay. So the fundamental theorem of calculus, to find the area under the graph of a non-negative continuous function f over the closed interval ab. Find any antiderivative f of x, capital F of x of lowercase f of x. The simplest one is the one for which the constant of integration is 0. All right, evaluate the antiderivative using b and a and compute f of b minus f of a. the result is going to be the area under the graph over the closed interval a to b, right? That's kind of a mouthful. I feel like this, is easier said than done. So we're about to start exploring some techniques for finding the integral. I think we've explored a few already, but let's keep going. In this example, we're asked to find the area under the graph over the closed interval from -1 to 2. Okay, I'll do a rough sketch. Just trying to think of how I want to do it. Let's do it like this. Space. I know I said a rough sketch, but we're gonna see how this goes. Okay. So x squared. I guess a few points shouldn't be too terribly bad. Let me see. Okay. So maybe let's go about here. Say this is the origin. Let me see. I'll make a quick table, right? So like x versus y. Let's see. Let's go -3, -2, -1, 0, 1, 2, and 3. Okay. What is that, like 9, 4? Nope. Back up. 10, 5, 2, 1. Right. 2, 5, 10. I think that's good. So x is okay. So then let's go 2, 4, 6, 8, 10, about like that. We'll drop down by 1. We can go 1, 2, 3, 4 is enough. 1, 2, 3, 4 is enough. Positive x is in this direction. Okay. Positive y is in this direction. Okay. Again, this is the positive y, this is the positive x. Let's see. So if we plot these guys, let's go this color. -3, 0. Oh, let's label it. So this is like the origin. This went 1, 2, 3, 4. 1, 2, 4, 2, 4, 6, 8, 10, 2. Okay. Okay. So then -3 and 10, 9. Yeah, 9 plus 1 is 10. And then let me do this real quick, like this. Yes, you are working today, like that. Okay. So then -3, 10 is here. So it's going like this. -2, 5 is here. 2, and then 1, and then the symmetry. Okay. And so we get, I'm just over from -1 to 2. Okay. So from -1 to 2, let's get rid of the extra stuff here. Get rid of this, get rid of that. -1 to 2, so from there to there. And we are, let's see something. We're getting something basically like this. And then let's go this one, partial. We can cut it like that, it's fine. Okay. Again, we got like this, like that, like that, and like that. Okay. So we're asked to find the area. Now that was, I'm just kind of doing this just for the sake of doing it. Let me do this one. This. I don't know if I can capture that shape. I don't know how I can get that shape exact. Okay, that's kind of close. Enter. That's fine. There. Come on. There. We kind of need some more points. That's fine. Can I? Is there a way to add a point? I don't know. I'm not gonna worry about it. Style, fill with that color. That's close enough. Oh, I know what I could do. I know exactly what I could do. Right here, partial. A little bigger. I'm not feeling that at all. Okay. Sorry, I'm just being a little bit OCD. Okay, that'll do for us so we can keep moving forward. Okay, that's fine. It's not the best, it's not the worst, so we'll get the job done. Okay, so this is what we're trying to find, right? So let me get rid of this extra stuff. Nope, undo. Let's go. Okay. All right, so find the area under the graph over this closed interval. So that, a little bit time consuming. You don't really need all that. I just feel like doing it. Okay. I guess we can start exploring the techniques now. I think last time we introduced the Riemann sum, but that's just an approximation. Yeah, I'm just going to go ahead and launch this technique. I'm not sure how they're doing it, but this is coming down the pipeline, so we can go ahead and talk about it. So, and I think we did one similar to this. The integral of, if we focus on that first term, x squared, right? The integral of this guy. We said what it was like x cubed over 3. So we're going to say like that's going to be x cubed over 3. The integral of a constant is the constant times x, so that's just going to be plus x. Now, before we did plus c, So I'm just going to go ahead and do this. This is also what's coming down. We want to evaluate this guy as x goes from -1 to 2. So normally it is plus c, but this is how we kind of evaluate definite integrals. And undo. Okay, that's I know that's going to act up. I'll just let that be. And so what we're evaluating is the integral as x goes from -1 to 2. Of this x squared plus 1 dx, right? So our integral of x squared is x cubed over 3. Integral of 1 is x. And we want to again, normally we do plus c, but for definite integrals, they essentially cancel each other out. So, and it'll show up as another constant, but you don't need it when you're doing this. And we want to evaluate this expression as x goes from -1 to 2. Let me see. So then all we're going to do, let x be 2, so that's going to be 2 cubed over 3 plus 2, minus, when x is a -1, -1 cubed over 3 minus 1. Okay? So that's 8 over 3. What is that, a 6 over 3? So let's just, if we distribute this negative, those both become positive. So then that's going to be a plus 1 over 3 plus 3 over 3, right? Let's see, 8 and 4 is 6 and 4 is 10, so that's 18. 18 over 3, which is what, 6. 6 units. Right? Okay. So I kind of just went on and launched into like integration techniques. I kind of want to see the way that the book did it. I kind of want to see the way the book did it, and we can break down what they did versus what we did. Okay. Let's see what they did. So find any antiderivative. Capital F of x for f of x. We choose the simplest one. Again, it says find any antiderivative. Again, normally it has the plus c. When you're doing definite integrals, you don't need it because when you evaluate the integrals, they cancel each other out essentially. or they get merged. You don't need it when you're doing the definite intervals. Substitute 2 and -1 to find the difference. They did exactly the same thing that we did. All right. So we got the same thing. So yeah, okay. Well, again, if you have questions, let me check the chat real quick. Chat looks okay. Q&A looks good. Let's keep the ball rolling. Let's try to get some more of these in there. That was good. Quick check I leave as an exercise for you. Maybe if we have time at the end, maybe we'll come back and work this one. Definition. Okay. So let f be any continuous function over the closed interval AB. And by closed, I just mean it includes the endpoints. If I say open, that means it doesn't include the endpoints. If I say the half interval, then that means one endpoint is included and the other endpoint is not included, right? So when I say closed interval, I'm saying we include those endpoints, right? That's what the square brackets are. So let f be any continuous function over the closed interval AB, and let capital F be any antiderivative of f. Then a definite integral of f from A to B is going to be, let me read this out for you. This is red. The integral as x goes from A to B of f of x dx is the antiderivative of f evaluated at B minus the antiderivative of f evaluated at A, right? So again, this is what we literally just did in the previous example. This is called a definite integral because we have those endpoints. We're evaluating the integral at those endpoints. Without that integrand symbol with the indices, the A and the B, then we would need the plus C, right? The constant of integration, okay? All right, so evaluate this integral as x goes from A to B. So in other words, they're just saying take the integral and then, evaluate it, right? So if we take the integral here, we just did this one. This one is x cubed over 3. We don't need the plus C here. And then we want to evaluate this as x goes from A to B. Now, they didn't give us A and B. So we're just going to say B cubed over 3 minus A cubed over 3. And that's as far as we can take it. Okay. So far, we've kind of been doing the same integration technique, right? The integral of a power function is 1 plus the power divided by the new power plus a constant. Except for indefinite integrals, you don't need the constant. Okay. Using the antiderivative, yada, yada, yada. It's convenient to use an intermediate notation. That's fine. Okay. Let me see, back up. So you can see the result in the center of the screen. I got the same thing as us. Okay. All right, let's look at this example 3. Evaluate each of the following. Okay, I think these are fun. So let's go like this. All right, so the first integral, again, x cubed over 3. The next one is going to be what? Minus x squared over 2. We want to evaluate this antiderivative as x goes from -1 to 4. Okay, so we plug in 4. 16 times 4 is 40 plus 24, 64. That's going to be 64 over 3 minus what? 16 over 2. And then we say what? Minus when x is -1. That's going to be -1 over 3 minus 1 over 2. Okay, so then we just do this evaluation. 6 and 4 is what? 10. I think I'm gonna just go ahead and get all the denominators to 6. So 128. 128 over 6. It's not an 8. 128 over 6. Let's try that one more time. 30 plus 18, 48. Is that right? 30, 40, 48. Okay. Minus 48 over 2. No, over 6. Double negative is positive. 2 over 6. Double negative is positive. 3 over 6. All right, you can use your calculator. You don't have to do all this. Let's see. 28, 20, 100, 80. 80 minus, no. 80 plus 5 is 85 over 6. We can leave it like that, to be honest. That should be okay. So when we did the first one, this is the result that we got. Now, I think that we actually can check this in our calculator. So I'm going to pull that up. I think we're good. It's actually saving my work. It usually doesn't do that. Okay, let's go here. Like, come on. There you go. Okay. All right. So what I'm going to do, this is a TI-83 plus. I'm going to go to my y equals. I'm going to say x squared minus x. Now, I think we can do this just because we're evaluating a definite interval. I just got to see if I can remember how to do it. Let me start off at math. Derivative. Okay. Now I have to remember the syntax. So evaluate that integral as x goes from -1 to 4. I think that's the syntax. We got what? I'm gonna hit math as a fraction. We got 85 over 6. 85 over 6. Look at God. Ow. Funny bone. Hit my funny bone. Anyway, but we got it, right? So we can at least evaluate definite integrals on a TI-83 plus. Now, it doesn't hurt to, you still need to know how to do it by hand because you don't always have that as an option. Just whenever you can, it's a nice alternative, but we don't always have that luxury, right? Let's recap. Let's just recap. All right, so we did the integral. All right, I think we talked about those integration techniques last time, so that's why I didn't go into those details. And we did not include the constant of integration because we're evaluating a different integral. Yeah, they did cancel out, right? Because there's no x. Yeah, there's no x there, so when you subtract them, they're going to cancel out. Right, and then so we evaluated that integral when x was 4, we get an answer. Then we say minus when x is -1, you get an answer. So the first answer minus the second answer, and we got 85 over 6. Okay, let's give part B a go. So I'll just kind of divvy it up like that. Let me see. So the integral of e to the x is itself, right? So that should be e to the x. Let me see. If you take the derivative, that's all you get. So when in doubt, when you take the integral and you get a result, you just take the derivative to check. So to check it, you just do a quick derivative. When I take the derivative of e to the x, I get e to the x. So we're good to go. I want to evaluate this antiderivative as x goes from 0 to 3. Okay, as x goes from 0 to 3. So then it's basically going to be e to the power of 3. E to the power of 0 is what? 1. So it's just going to be e to the power of 3 minus 1. Okay. Let me see. So then if we wanted to check this in our calculator, right? If I go to my y equals, I'll clear out the first one. I'm just going to put e to the power of x, close parentheses. And then I'm going to recall what I had before. So I want to evaluate the integral of that function as x goes from 0 to 3. So I need to change my indices. This needs to be 0 to 3. Now we're going to get a decimal. And we just need to make sure that the exact form is the same decimal. So what we're going to do is say e to the power of 3 minus 1. And we should get the exact same decimal. Right? So we got it. All right, so this last one. Okay, let's try the same thing. So still just more integration. So the integral of a constant is the constant times x. So that was just the first integral was just gonna be x. Integral of 2x is what? 2x squared over 2, which is just x squared. right? Because if you take the derivative, now you get your 2x back. The integral of 1 over x, I think, is ln, is natural log. So minus the natural log of x, right? So that's a special case when you have 1 over x. Okay. We want to evaluate this antiderivative as x goes from 1 to e. If you're just joining us, here we're not adding the constant of integration. We're not adding the plus c because we're evaluating the definite interval. So we say the upper index minus the lower index, the constant of integration cancels out, so we don't need it here. All right. Hopefully, I know that there'd be a lot to process if you're just joining us, but you know. So we want to evaluate this antiderivative when x is e. We get an answer. We're going to say minus, evaluate this when x is 1. So the first answer minus the second answer. Okay. Okay, let's keep going. Like this. So then we're going to have, that's going to give us, hang on. Go. Okay. So when x is e, we're going to have what? E plus e squared. Natural log of e, they cancel, so that's going to be a minus 1. So that's the first answer. Minus, with the lower index, we get a 1 plus 1. Natural log of 1 is 0, so like that. So negative 1 minus 2 is a negative 3. So the exact answer we get is e plus e squared minus 3. Okay. And again, something like this, we can check in a calculator. You know, we can at least confirm that we're pretty much there. Let's just check like we did the previous. So then the original, we had this 1 plus 2x minus 1 over x. Okay. That looks good. I'm just going to recall what we did before. I want to take the integral of that function as x goes from 1 to e. So I need to change both of these guys. This needs to go from 1 to e. Okay, this is good like that. Okay, that should be okay. Actually, let me insert a 1 here. Okay, now we're going to get some long decimal. And then we put in our answer, and we should get the same decimal. Plus e squared minus 3. And right, we got it. Okay. So now we'll check and compare it to the prepared notes just to confirm that these numbers are correct, or make sure that we are on the right track. But with this whole experience, and I know at this point this is kind of like a mute point, I guess. But just try to process whatever you can. Don't try to follow every excruciating detail that I do. Just try to get the gist of it. And again, it doesn't really sink in until you go to practice it on your own. I would imagine by now that hopefully you guys have some kind of system where you're collaborating. You got a tutor or a classmate, or one of the Morehouse tutors, or something. I'm just hoping that you guys have something like that. And just do your best and just kind of get everything submitted, and you should be okay. All right, let's keep going. All right, so the first one, 85 over 6. So 6 is 40 plus 24 is 64, 65? 60, no, 85 over 60. Yeah, I think we're good. I think we're good on that one. Okay. E cubed, yeah, we got that same thing, and same thing here. Okay. So I got a good amount of slides. Let's keep going. Quick check is an exercise for you all. All right, so we have this thing that says the fundamental theorem of integral calculus. If a continuous function f has an antiderivative over a closed interval ab, then the limit as n tends to infinity. So this is basically the summation of the Riemann sums, those little rectangles we had from last time under the rectangle, is equal to. So now we're taking the limit as n tends to infinity. of these Riemann sums. So remember when we introduced Riemann sums, we had like one where we had 6 subintervals, and then we had the exact same question, but with 12 subintervals. And the conclusion that we arrived to was that the more subintervals we have, the better our approximation. So this is a way. So basically, we're saying, okay, so suppose you can have infinite subintervals, like you can just jam pack to the limit, right? If you take it, the limit as n tends to infinity. In other words, infinite subintervals. That's exactly equal to the integral of the function as x goes from a to b of the function, of f of x dx, right? Which is going to be the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. Long story short, the Riemann sums we had from last time, instead of, again, if we took the limit as n tends to infinity. Now that left part is just like for a formality. We don't really do anything there. We're pretty much with that center. We're working with that expression in the center. All right. It's just saying conceptually that's what we're doing, but we're using these integration techniques in the center like we've been doing. All right. Okay. All right. So suppose that y is the profit per mile travel, and x is the number of miles traveled in thousands. Find the area under this curve over the closed interval from 1 to 4 and interpret the significance of this area. Profit per mile, number of miles traveled. Okay, so it seems profit. So it seems like the more miles you travel, the less profit you make. Okay. Long story short, it says find the area under this curve over the closed interval from 1 to 4 and interpret the significance. Okay. Area, profit per mile. So would that be like the total profit that you would earn if you travel between, would that be the total? I think it would be the total. Okay, anyway, let's find the integral. All right. So we want to take the integral as x goes from 1 to 4 of this function, which is 1 over x dx. So we're basically taking this integral. Now, in the previous example today, we said that what the integral of 1 over x is the natural log. So that's going to be the natural log of x as x goes from 1 to 4. Right? We want to evaluate this antiderivative as x goes from 1 to 4. So then that'll be what? The natural log of 4 minus the natural log of 1 is what? 0. That's a special case, right? So it's just the natural log of 4, whatever that number is. Oh, did my pen just die? No, why are you not working? Okay. So we got a result of natural log of 4. We use our calculator to get an approximation. So the total, I'm thinking the total profit earned if you travel from 1 to 4 miles, something like that. Let's see how the book articulates what that is. So we got the same thing, natural log of 4. Use your calculator to crunch that number. The area represents a total profit of 1386. Let me see, thousands, right? So profit per mile in dollars, number of miles traveled in thousands of miles. Okay, so that means that your result you got to multiply by 1,000. 1, 2, 3. So 1386. 1386.30 when the miles travel increases from 1,000 to 4,000 miles. Okay. Okay. What's the time? Okay, let's keep going. So consider this function. Predict the sign of the integral by examining the graph and then evaluate the integral. Okay. So we have the brown part is above the x-axis, and the orange part, it seems like there's more of the graph that's below the x-axis versus the amount that's above. So we would anticipate the result to be negative, right? That's a reasonable conclusion, right? So let's see if that's what happens when we take this integral. All right, let's give it a go. Okay, so the integral of x cubed is going to be what? X to the 4 over 4. So it's going to be what? Negative x to the 4 over 4. The next one is going to be what? 3x squared over 2. So then plus 3x squared over 2. minus x. Okay. And then we want to evaluate this antiderivative as x goes from -1 to 2. Okay. So if we plug in when x is 2, 16, so it's a -16 over 4. 4 times 3 is 12. 12 over 2 is the same as 24 over 4. Minus 2 over 1, so then 8 over 2. I mean 8 over 4. Right, I just got a common denominator. Okay, so that's the result. That's from the upper index, right? So then we're going to say minus. Oh, come on. Let me unplug it. Part of the reason it's kind of trippy if it's charging while I'm trying to use it, it just those tantrums. So we're going to say minus. Oh, come on. Why? I think my pen also might need to charge. Let me charge it. Come on. All right. Let me see. Oh, okay. Maybe it's because I need to do this. Okay. Let's try this one more time. Minus. There we go. All right. Minus. Now we want to evaluate this when x is -1. So that first one's going to stay as a -1 over 4. Okay. That's going to be a plus 3 over 2. So then what, 6 over 4? So plus 6 over 4. So double negative is a positive, so that's like a plus 1, so plus 4 over 4. Okay. I'm just going to go ahead and distribute my negative before I crunch the numbers. So this is going to be a positive, positive. That's going to be a negative, and a negative. All right. Okay. So now I can just combine all these numbers, all right? So we got a -16. What is that? 4 and 4. That's a positive 8 minus 8. So that's a 0. So all of this is gone. All right. Does that all go to 0? And then -10 plus 1 is a -9. So it looks like I'm getting a result of -9 over 4, which is what we anticipated. Right? We were anticipating a negative result because most of the graph was below the x-axis between -1 and 2. Okay. So we got this result. All right, let's see how do we do. All right, so considering this integral, predict the sign and evaluate the integral. Okay, so from the graph, it appears that there's considerably more area below the x-axis than above. So therefore, we expect the sign of the integral will be negative. Okay, we had the same conclusion. 9 over 4, so 4 times 2 is 8, 9 over 4. Yep, so then we got the same thing. We got 10 slides. Still got a good amount of time. Let's keep going. Let's keep going. Example 6. Are there any questions? Let me check the chat. You guys are so quiet. It makes me nervous. But again, I've just, I kind of let it be. I'll be right back. Give me just a moment. Oh, good job. So this is one of the things I appreciate about being remote. Like thirsty, so I went and got myself something to drink. If I'm in class, I was like, damn, I want to drink that water fountain water. I would not drink that. But at home, I have my comfort stuff, so food and bathroom and hammock and stuff. All right. So let's give this one a go. So Northeast Airlines determines that the marginal profit resulting from the sale of X seats on a jet traveling from Atlanta to Kansas City in hundreds of dollars is given by this. So marginal profit, so that's a derivative, right? Find the total profit when 60 seats are sold. In other words, they're asking us to take the integral. That'll give us a total profit, and then evaluate the result when X is 60. Okay. Okay, I'm going to do something here. I am going to move this around just a smidge. So I'm going to take it from like here. Like so, like that, like so, like that. Maybe more like this. That's decent. And I'm going to take that and drop it right. Sure. First, let me match up the size. That's decent. That's good enough. And I'm just going to slide this over just like that. Boom. Crop this one. Okay. All right. Okay. So long story short, we want to evaluate what? Find the total profit when 60 seats are sold. Okay. So we're going to do the definite integral. We're going to say we want to find the integral as x goes from 0 to 60 of this function dx. Okay. So x, the square root of x is the same as what? X to the power of a half. So then we can use the power rule. So it's going to become x to the power of 3 halves over 3 halves minus 6x. Okay, we want to evaluate this as x goes from 0 to 60. Okay, so when you plug in 0, all of that's gone. So then I'll just keep working over here. Square root of 60, cube root 60. So, I mean, we essentially have, let me think. 60 is what, 6 times 10? I'm going to write it like this. 3 and a 5, 10, 6. So there's only a 2 in there. I'm going to evaluate the square root first and then cube my result. Okay, so 2 times the square root of 15. Actually, I think I'm going to do it the reverse direction. Because you kind of have an option to either take the square root first and then cube your final answer. If I cube this, then I just have 3 of everything, right? Let me see. Like this. This is a little bit extra. You don't have to do all this. I'm just playing around. All right. And then we would take the square root. So then how many groups of 2? Like, I should have put it in order, but here's one group of 2, a second group, a third group. Here's a group of 2. Here's a group of 2. Okay. So let me see. 4, 16, 64. Is that an 8? 8 times 3 times 5. Is that right? Why does that feel too big? 8 times 3 times 5. 8 times 5 is 40, so 120. Okay, that might be the case. Okay, so we got 120 times the square root of 15 over 3 over 2. 36 minus 3600. 360. 240 divided by 3 is 80. Okay. So I'm getting an exact result 240 divided by 3 is, I'm getting 80 times the square root of 15 minus 360 as an exact result. Okay, let's see. Find the total profit when 60 seats were sold. So we're just going to use a calculator to crunch that number. Let's see. Let's see. How did we do? So I got 80 times the square root of 15 minus 360. Hopefully it's not negative. Oh, well, that could be the case though. The total profit, we're in the hole by 50. What are the units here? Total profit. Okay, here. Determine the market to sell X seats on the jet travelers in hundreds of dollars. All right, so we got the tack on 2 zeros, so 5,000, or just move the decimal, $5,016.13. So we're in the hole. I like 5,000. Well, we got past the hardest part. We interpreted it incorrectly as far as those units, but everything else we did was fine. Let's see, theirs looks a little bit more simple. No, they just used the calculator at that point. Okay, here's the explanation. So when 60 seats are sold, Northeast profit is going. Oh, we got it right. Minus the 5,016.13. That is, the airline would lose 5,000 on the flight when only 60 seats are sold. And I guess that makes sense, right? Because you know they want to be the capacity to maximize profit. Speaking of like companies maximizing profit, so apparently, like cruise lines, they lose money. Like same scenario here. Like if they don't fill those empty seats or whatever, they lose a lot of money. I haven't tested officially yet, but supposedly there's a site. You have to do your own research and just be careful. But it's what is it? I think it's vacation.com, and they were like, you go and change the settings so that it's like cruises that leave in the next 90 days. And so again, within 90 days, those companies, they don't want an empty cabin. So you can get them reduced like up to like 90% reduced or something like that. Vacations. I was playing around with it the other day. I was like, oh my goodness, this is real. So, just kind of be careful, do your best. But yeah, I think what we got is fine. So I'll include the screenshot. Where to go? I'll just do this instead of trying to run it out. I tend to like avoid Instagram. I don't know. I'm not really on social media like that. Most social media I do is like YouTube, and I don't even know if you really consider that social media. But for the little bit of time that I am on Instagram, I think that's where I saw that little promo. I'll just shrink it down a little bit here. Okay, so that's at least included if you're ever to go pull these notes. Okay, we still got a good amount of time. Let's kind of keep going. I think once we finish this section, that'll be enough for the day. Okay. So they essentially did the same thing we did, evaluated the integral as x went from 0 to 60 of the function that was given. I think they got the same result that we got. And then notice that part on the right-hand side, it goes to 0. So all of this collapses to 0. So then it was just a matter of simplifying this expression on the left, and we got the same result. And then we had to interpret it. So when 60 seats were sold, Northeast profit is down by $5,000. That is, the airline will lose this much on that flight. And it's so funny, when I went to crunch the number, I was like, man, I was getting the vibe it was going to be negative. I was like, I hope it's not negative. And then we got a negative, and I kind of panicked for a split second. I was like, wait a minute. It could be negative, right? What does that mean if it's negative in this context? And so I'm all giddy because, like, once I get out with you guys, my weekend starts. So now I'm like, okay, what am I doing with my time? I'm gonna go here, I'm gonna run it there. So I just be in my own world. Like when I'm not with you guys, that's why it's like I try to go ahead and do my stuff while it's on my mind. Because otherwise, like from the moment I leave you guys on Wednesday till we meet again on the following Monday, it's a blur. Like it's a total blur. But yeah, anywho. Okay, we're almost done actually. Let's keep going. Quick check. That's gonna eat up a lot of slides. Not enough though. All right, so we have this example 7. It says that a particle starts out from some origin. Its velocity in miles per hour is given here, where t is the number of hours since the particle left the origin. How far does the particle travel during the second, third, and fourth hours? From 1 to 4. Okay. So long story short, it just seems like they're asking us to evaluate the integral as x goes from 1 to 4, and then interpret the results. Miles per hour. Okay. So I'm going to generate a little bit of space like I did previously. Just kind of reposition it a bit. And like, I don't know, I mean, I've been in Atlanta my whole life, but I swear every time I turn around, I'm always discovering something else to like explore in the city. And it's just, from free stuff to just like a whole bunch of stuff. And it's like, damn, you can't really get bored. I mean, you can, but I kind of find ways around stuff, like just free stuff. And I try to pay for subscription to things as much as possible, so that way, like for a little bit of times when my money's low, and I'm not trying to spend money. Well, I was like, well, it's already paid for, so let me just go and enjoy myself. Okay, all right, we're gonna go here. Okay, so what it's asking us, evaluate the integral as x goes from 1 to 4 of this function, square root. I really do not feel like dealing with the square root, but it's fine. Right, dt. Okay. So t to the half, so that's going to become, we can write it as 2/3 t to the power of 3 over 2, right? Because when you divide by 3 over 2, you multiply by the reciprocal, plus t squared over 2. We want to evaluate this as t goes from 1 to 4. Okay. So then when t is 4, the square root of 4 is 2. 2 cubed is what? 8 times 2. So that's going to be 16 over 3. When x is 4. When t is 4. Plus 16 over 2 is 8 over 1. So 24 over 3. Okay. So when we plug in a 4, we got those results. Then we're going to say minus, we're going to plug in when t is 1. So that's going to be 2/3 plus a half. That half is the one that's throwing things off. We almost got them all to be. Did I do the? You know what? I think yeah, because we got 8, right? We plugged in a 4. 4 squared is 16 divided by 2 is 8. So then we got a common denominator. Can we get that to a denominator of 3? No. It would be weird. I'm gonna get them all to 6. So what is that? 32 over, no, that's not a 2. 32 over 6, right? 48 over 6. I'll go ahead and distribute my negative as well. Times 2, so minus 4 over 6 minus 3 over 6. Okay, so that's a minus 7. That's a positive 41, 71, 73 over 6. 11, 12 will be 72. And 1 over 6 miles. How far? 12 and 1/6 miles. Particle starts off, velocity is given by this guy. T is the number of hours since it left the origin. Hours, miles per hour. 12 miles in 4 hours? What kind of particle is this? Molasses particle? How far does it travel? Let's see. How do we do? Did we get these numbers right? Let's just check. Velocity of speed is a rate of change in distance with respect to time. In other words, the velocity is the derivative of the distance, and the distance function is the antiderivative of the velocity. To find the total distance, we evaluate. Did we do from 1 to 4? We did from 1 to 4. Yeah, yeah, we did that. 12 and 6 miles. What kind of particle is this? Now I'm like, my interest is peaked. Right. Anyway, we got 15. Okay, it's fine. All right. Okay, well, got the exact same thing. Let's gotta take a moment to go through the summary and we'll close out and call it a day. So the exact area between x and the graph of the non-negative continuous function over the closed interval is found by evaluating the definite interval as the interval as x goes from a to b of f of x dx is going to be the antiderivative of the function evaluated when x is at b minus the antiderivative of the function when x is a, all right, where f is the antiderivative of f. If a function has areas both below and above the x-axis, the definite integral gives the net total area or the difference between the sum of the areas above the x-axis and the sum of the areas below the x-axis, right? So we saw it gives the net difference between the sum of the two areas. So if we take the area above minus the area below, then the total area gives us the net difference between the two. If there is more area above the x-axis than below, it's going to be positive. If there's more area below the x-axis than above, the interval will be negative. If the areas above and below the x-axis are the same, the interval will be 0. That's interesting. Are there any burning questions before we go our separate ways? We're out a little bit early. Yeah, I can't think of anything. So just kind of keep working. If you have questions, you know how to reach me. Make use of my office cell phone number. Also, as you kind of going through the assignments, you can make use of the whole ask my instructor if you want my response. Like mine is going to be kind of like I would do it in class. And hopefully by now, again, you guys either have a classmate or a tutor, or you figure something out that's working for you. Okay. If there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, have a great weekend, gentlemen, and we'll meet back on Monday for the next installment. All right, guys.
Professor.
You as well.
Yeah, have a good weekend.
You as well.
We're going.
Go ahead and do this attendance. Any other questions going once? Going twice? Your peas and rice. All right, guys. Take care.